So um, I'm assuming you can all see my screen. Hey, Brandon, turn off your mic. Um, the homework is officially due tonight. If you're struggling with it and need a little bit of extra time, we can talk about it later. We'll talk about all that stuff after the lecture. If you have questions, though, about the lecture material as I lecture, please let me know. You're welcome, Eric. And okay. So this class is about motion. It's on kinematics and dynamics, which are ways to say the motion of a particle or a system. In this chapter, we're going to introduce how to mathematically describe motion. At the beginning, it's going to seem probably really simplistic. So bear with me. It'll get complex pretty fast. But we need to be able to describe in a mathematical way motion. And we're going to do that to start off with doing one-dimensional motion. And then from there, we'll talk about what happens in 2 dimensions and 3 dimensions. And really, though, this chapter, I really want to introduce what I call an algorithm for solving problems. And the problem is that many people who are good at, say, math or good at chemistry, they find that in physics, they don't know how to start problems. And so one of my main goals in this course, for each chapter, I kind of want to work on getting you algorithms or recipes or just a standard set of steps to follow when you're confronted with a particular kind of problem. So that at the very least, you can start the problem and maybe you can make, you can get somewhere, you can start finding some of the answers. And so we'll talk about what that algorithm is for one-dimensional motion problems. Next week, we will talk about Newton's laws. We're not going to talk about Newton's laws today. Today, we're going to just try to understand what it means when you have velocity and acceleration and displacement and how those things work together mathematically to give us a model or a mathematical equations that will tell us something about the motion of a particle. And the fun thing is, the last set we're going to do is free fall, and you can actually test that right now while you're on your computer. You can turn your phone on to the stopwatch and drop things and figure out like what the acceleration is of gravity where you are. It's pretty fun. But anyway, moving on. So the first thing you need to understand is, let's say you have a particle that starts at x is equal to 0 and it travels to x is equal to 10 meters. So it goes this whole distance. We call that the displacement of a particle. So displacement is the change of x, or x final minus x initial. And here, what we get is 10 minus 0. And you can put meters in there if you want. Whenever we have this triangle x or triangle t or triangle y, it always means final minus initial. These little subscripts mean final and initial. We use 0. I don't know why they use 0 for initial, but this doesn't have to be 0. This could be 2 and this could be 12, and we'd still get 10 meters of displacement, okay? So all you're doing is you're describing how far the object traveled in the x or the y or the z. So this could be delta y or delta z or delta whatever, delta r. Displacement is just the change of position. Now, what happens though if we want to measure how long it took to go r 0 to 10? And let's say we have a stopwatch and we measure that it took 3 seconds, okay? When we do that, we get something called the average velocity. And the average velocity is the change of position over the change of time. And I should tell you that we would say t final minus t initial, but we almost always assume that t initial is 0. So when we say delta t, we really just mean t. We mean the elapsed time. So here what you get is you get 10 minus 0 over 3. because this is x is equal to 0 and this is x is equal to 10. So it went 10 minus 0 in 3 seconds, and we get, what is that, 3.33, you know, whatever, meters per second, because these are meters and these are seconds. So velocity is always position over time, and the average velocity, you just take however far you traveled and you divide it by the amount of time it took. I think that's easy to understand, right? If you went jogging this morning and you jogged 10 blocks in 10 minutes, your average velocity was 1 block per minute. The problem with average velocity is that it doesn't tell us a whole lot. Average velocity is sometimes referred to as speed. And what I should say is that velocity is really a vector. So we might say, well, what was your average velocity in the x direction? And we put this. Here's the thing though. I don't like putting x hats and unit vectors on vectors. The reason why is I find it's distracting to you guys. I also find that it's not necessarily helpful to remember for us. And when you get to 4B, it actually gets really confusing because the vectors are all from a radius. So if I drop an x hat on a vector, I'm going to assume that you know it's a vector. You know that velocity is always a vector. It is the displacement over time in a certain direction. So we could have a velocity in x, we can have a velocity in y, we can have a velocity in z. Most vectors, I'm going to assume you know they're vectors. I might put the little hat sometimes, but I tend to drop it just because we know what vectors are. And now speed is actually the magnitude of the average velocity, okay? And it's not a vector, it's just a number. If I said that I was doing 10 miles per hour on the way to work, that means my speed was 10 miles per hour. If I say I traveled 10 miles per hour north for 10 seconds, and then I traveled 10 miles per hour east for 10 seconds, those are vectors. Speed is simply a magnitude, and it's utterly useless in physics because it doesn't give us any information. It just tells us a number. And so the problem is most of you probably use speed when you mean velocity, and there is a big difference between the two. Velocity is a direction. Speed is just a number. Don't worry too much about it, but in Wiley, they'll ask for the speed on some homework problems. And what they mean when they say that is they mean the magnitude. They don't mean a direction. Okay, so that's all well and good. If we want an acceleration, and this gets a little bit challenging too, because it's probably something you've used all your life. You've used the word acceleration when you actually meant speed. What acceleration is, at least average acceleration, we use a little a for it, is it's the change of velocity over the change of time. So if we started here and our velocity was 0 because we started at rest, and here we were doing 3.33, our change in velocity would be 3.33 meters per second minus 0 over 3 seconds, or 1.11 meters per second divided by seconds, which is 1.11 meters per second squared. Again, this is a vector. It's in the positive x direction in our example. So acceleration is the change of your speed. That's actually kind of hard for humans to always grasp, that it's how much your speed changes. Your velocity is pretty easy. You realize how fast your position changing with time is your velocity. But how fast that velocity changing with time is your acceleration. So when we say a car accelerates from rest at like 6 meters per second squared, what we're saying is how fast it gets up to a certain velocity. And that takes a little bit of imagining. Some of you probably have it. Most of you probably have that firmly in your head, what acceleration is. But for some of you, you've been using acceleration when you meant velocity. And so you need to get that out of your head. We are always going to talk about acceleration in this class because we're going to define a force as mass times acceleration, and we'll talk about that next time. But if we define a force as an acceleration, we can then do certain things like integrate or take derivatives and find velocities. And from velocities, we can find the position of a particle and describe the motion of what's going on. So we need to be really clear on what acceleration is. Secondly, we really don't care about average velocities. And that's because if you jogged around your block, you might tell me how fast you went on average, that you went, 3 miles in a half an hour. So you went 6 miles per minute or 6 miles per hour. But what I really want to know is I want to know what the velocity is at a given moment in time. So let's say I have some equation, let me take that back. This depends on time for my x position. And let's say this is 4x squared minus 2x plus 8, okay? So I have, those aren't x's, those should be t's. I'm sorry, guys. T and t, okay? So if I want to know the velocity at any time from that equation, what do? What is the instantaneous velocity of a position function? Well, it's quite simple. The instantaneous velocity is the derivative with respect to time of your position function. In this class, a lot of times, we're not even going to need to take it. We're going to need to use this to derive equations, but in general, you're not going to actually be computing that derivative except at certain times. However, we could, and we should. So if we take the time derivative of this, 8 doesn't depend on t. The time derivative of this is minus 2, and the time derivative of this is 8t. So you can see that my instantaneous velocity at some time is 8t minus 2. It's the time rate of change, which is also called the derivative of x at a particular t. So I could say, well, what is it when t is 1 second? And what is it when t is 10 seconds, right? At 1 second, this would be my velocity at 1 second when t is equal to 1 would be 8 minus 2, or 6 meters per second. My velocity at 10 seconds would be 80 minus 2, or 78 meters per second, okay? So the velocity in mathematical terms, in calculus terms, you've all learned derivatives, is the time derivative of a position function, okay? Now, to make that more clear, that x position that I gave you, this is an x versus t graph. You should know from the lab report what we did on graphing that x versus t means x is on the y, t is on the x. And this function, if I go back and I look at, well, when t is 0, I'm at 8, and then it does some kind of parabolic thing. So it probably, I don't know what this actually is going to look like. It's going to do something weird, right? However, if I want the slope at any point here, at any instantaneous point, the slope is tangential to the line, okay? And let's say this is, I don't know, and it's not going to match up with the derivatives I take, but I'm making this up. Let's say this is T1 and this is T2 and this is like T5. What this tells me, what the slope tells me, remember when you have a line, this is mx plus b. Well, b is 0. It's the intercept. We're going to assume it's not 0 here, here it's 8, but for now, just assume that's true. Then the slope, m, is y over x. And on an x versus t graph, if I took some region, say from 1 to 2, I would get the average velocity because I would get delta x over delta t, right? But at a point, I would get d dt of x, which is my velocity. So my slope at any point of a graph of x versus t is my instantaneous velocity at that point. That's actually section 6. It's pretty easy to understand. The instantaneous acceleration, exactly the same, except now it's the time rate of change of the velocity function. And we found that here to be 8t minus 2. So we said that vt was 8t minus 2. And we find that when we take the derivative with respect to time, nothing happens here because it's constant, we get 8. So this would equal 8 meters per second squared. It's constant in this case. The instantaneous acceleration at any time is the time derivative of the velocity function. In this case, it's a constant acceleration, okay? So if it were 0, if the velocity were constant, so if v of t were, let's say, 4 meters per second, doesn't depend on t, then a of t, which is dv dt of dt, would be 0. Sorry. That tells us that if we have constant velocity, then we have no acceleration. And that should make sense to you in words. The velocity isn't changing, so the time rate of change of the velocity is 0. There's no change of the velocity if the velocity is constant. You could also say that about the position. If the position is constant, if it's not moving, there's no velocity change, right? So we never talk about constant position, but we will talk about constant velocity means a is 0. And we'll get there in a little bit. So all that's well and good. We now have that the position is change of x, which was x final minus x initial. The average velocity is the change of position over the change of time. The instant velocity is the time rate of change or derivative of some position function. The average acceleration is the change of v over the change of t, and a instant is ddt of v of t. Now, practically, and I should say that on the next slide, I'm going to skip the next slide, but if I had a v versus t graph, the slope at any point would be the acceleration, okay? So the slope of a v versus t graph is the same as dv dt, right? I think you guys know how to do that. You've learned it in calculus. I don't really particularly need to go over it. What I do need to talk to you about, though, is that I could give you some weird position function, like this is x squared sine squared of, sorry, keep doing that, t squared sine of omega t plus ln of t and blah, blah, blah. I'm not going to do that. We'll talk about it in a minute, but in general, we're going to have pretty simple functions that you should be able to do the derivatives of really fast. However, if you had some weird function of x, you could take the derivative once and get the velocity. You could take the derivative again, so v is dx dt, and a is dv dt, or the second derivative with respect to time of the position. So if you took the derivative twice of the position, you would get the acceleration. The acceleration is the time rate of change of the time rate of change of the position, or the time rate of change of the velocity. So it's pretty simple in terms of all of that, okay? The other thing I should note is that you can have, let's say, I have something that's moving, if this is in the x and this is in the y, and it's got some velocity at, say, 30 degrees. I can have a vy and I can have a Vx. This is a vector. All you have to do is, this is V sine of 30 degrees. This is V cos of 30 degrees. You can put the little y hat if you want. And then the magnitude is the magnitude of Vx squared plus Vy squared. And you can see that pretty easily. The nice thing about it, though, is we can treat the x as its own dimension and not worry about the y. The velocity in the x is independent of what's happening in the y. The velocity in the y is independent of what's happening in the x. Same with the acceleration. We can do everything in the x dimension, do everything in the y dimension, and then put them all together later. So in this chapter, we're only going to talk about one dimension. We're going to talk about x, and when we talk about free fall, we're going to talk about y. But starting chapter 3, when we talk about parabolic motion or parabolic motion, projectile motion is what I was trying to think of. When we talk about projectiles, we will be talking about x and y independent of each other and adding them together. You're going to see that, though, in some problems that we do at the end of this. Okay. The last thing that I need to do before we start doing some problems and knocking out some fun problems is what happens when we have constant acceleration. Now, I already said that A was dv dt. And so I see that dv is equal to A dt, except I'm assuming A is a constant and not 0. I don't know what that constant is. I don't care what that constant is. I'm going to derive an equation for the velocity out of this. So I need to put limits on this and integrate from V initial to V final. Over here, I would have to integrate from time initial to time final. But I'm always going to assume this is 0, and I'm just going to call this t. Okay, that might be a little weird for some of you math people, but that's what I'm going to do to get the equations in the form that you're given in the book. Now, this is quite simple, right? There's no variable here, so it just becomes v when you integrate it, and from v final minus v initial. V final minus v initial. I'm actually going to call this, though, v minus v initial, and you'll see why in a second. Now this becomes at, right? It would be at final minus t initial, but t initial is 0, and we're calling t final t. So we have this equation. And this equation with the v final is actually our first equation. The change in velocity is equal to the constant acceleration times time, okay? So let me write it this way and do one of these really fast for you. Your car or motorcycle might have an acceleration of 6 meters per second squared. And let's say we want to know after 4 seconds what your final speed is. And you start from rest. Rest means that v initial is 0. So we want to know what is v final, or v in this equation. So all we get is v, I hate when my stupid thing does that. We get v is equal to v initial plus at. Plugging these things in, this is 0, and we get 6 times 4, which is 24 meters per second. In whatever direction the acceleration was in. So we could say, oh, this is starting at the origin and going in the positive x direction. So these are v final of x and v initial of x and a of x and a of x. I'm just keeping it pretty general. But if you did that, it would be in the x hat direction, right? And so what you see is the acceleration, if it's constant, times time, gives you the change in velocity. We got that from the integrals. Now, we can go further though, because now that we know that v is v naught plus at, we know that v is dx dt. This is our instantaneous velocity is dx over dt. From that, we get that dx is v dt. We can again do x initial, x final, and t initial is 0 and t final is t. And now I'm going to substitute, though, in for v my equation here. So I get 0 to t, and I get v naught plus at times dt. Again, simple integrals, right? We get x final minus x initial is equal to v naught t plus at squared over 2. When you integrate x, you add 1 to the exponent and divide by the new exponent. So we add 1 and we get 2 and we divide by the new exponent. This is our equation for the position, right? And we said that a was 6 and t was 4. So a was 6 in the x direction, t was 4 seconds. We can find the position after 4 seconds, assuming that it starts from rest at position 0. So this goes away, this goes away. And what we get is that x final is a t squared over 2, which would be 6 over 2 times 4 squared. 3 times 16 is 48, right? 48 meters. So we can integrate, technically we could integrate any acceleration and any velocity to get the position functions. However, we're going to talk about constant velocity, and this equation is true if a is a constant term. If a were not, you would have a different variable or a different equation come out of that. So the point here is that we're using constant acceleration equations, and we already have 2, that v final minus v initial is at, and x final minus x initial is v naught t plus at squared over 2. We're going to use constant acceleration a lot in this course. The reason why is that we're going to assume our forces are being applied constantly, okay? So we're going to have constant forces, and if the force is constant and it's equal to ma, well, the mass is constant, obviously, so the acceleration has to be constant. And so these equations apply whenever you have a constant acceleration. They also apply in the x, in the y, in the z. So if you have a constant acceleration in the x, you have these equations. If it were a were actually in the y hat direction, then you'd have v final of y minus v initial of y is equal to ay times t. Y final minus y initial is v naught y t plus ay t squared over 2, et cetera, et cetera, et cetera. You know, you could have z. They apply in each direction. So you'd have a set of equations for the x, a set of equations for the y, and a set of equations for z. On and on and on. If it were not constant acceleration, say this were a were x t squared, I'm sorry, a were 4 t squared was our acceleration. All you'd have to do is you would get v dv is equal to a dt. Take those same integrals, v naught to v final, 0 to t, and what we get is v final minus v initial is, if this were 4t squared, this would be 4/3 t cubed, right? And then you could do the same for the position. So it doesn't really matter if a is not constant. All you do is do the integrals, but we're not going to do those. We're actually going to use these constant acceleration equations. If you've had physics before, you've probably seen something very similar for projectile motion. These are the general form. If the acceleration was 2, you would plug in for a 2. If the acceleration was -2, you'd plug in -2, -2. That's going to be important soon. And I'll show you that in a minute. So we're now ready. Well, not quite ready. Let me actually add one thing that I haven't talked about. So we have, let's say just for the x direction, we have that v final is equal to v initial plus at and x final minus x initial is equal to v naught t plus a t squared over 2. And this is going to assume that a is in the x and b final and b initial, or all of those are all in one dimension. We can actually make more equations out of this by substituting. You could solve this for v naught and plug it in here, and we would get 2 other equations that are important. We get x final minus x initial is equal to v final plus v initial over 2 times t. I'll let you do that. All it is substituting in, and then solve this equation for a and put it in here, and you get this equation out. Solve this equation for v naught and put it in, and you get this equation. There's a little bit of algebra here that needs to be done, but for the most part, it's pretty easy. But let's look at these equations really fast. There's something really important going on here. This equation is what I call the big equation. And the reason why it's a big equation is we have x initial, x final, v initial, v final, a, and t. That equation that I boxed has all 4 of those. Well, it doesn't have v final, so this is really no v final. And for whatever weird reason, your book is the only book I've ever seen do this. They give you an equation where they substitute in to get v final in here. You can do that, but I would just leave it alone. So this big equation has no v final. This equation, you'll notice, has no x. This equation, you'll notice, has no a. We're going to come back to this. And this equation has no t. So we basically, if we didn't know the time in a particular problem, we'll know to go right to that equation. And if we don't know the acceleration and we don't want to find it, we know to go right to this equation here, on and on and on. So generally, the reason you have these 4 equations is so that you can use whichever one you need. And we'll talk about how to find that in a minute. The last thing I want to talk about really fast before we start doing problems and looking at the algorithm is, what if a is 0? What do we get here? If a is 0, we get that v final is equal to v initial. Of course we do. If a is 0, the velocity doesn't change. So the velocity is always just v. If a is 0, we get x final minus x initial is equal to v naught times t, or v final, or v, whatever it is, because v is always the same value. This equation, if v final and v initial are the same, this becomes 2v divided by 2. It becomes vt, which is exactly what this is. We can just call this vt, where v is v naught or v final, since they're always constant. And if a is 0, this says that v final squared is equal to v initial squared. So there would be a sign. So technically, this would be plus or minus v initial, but we'll assume it's positive. So what I've done, and I'll show you these on the last slide for you, is I've assembled these equations, and then we have the free fall ones. We'll talk about those in a minute, but I've given you those. Pretty much, we're going to add 2 or 3 other equations to this, but pretty much we have all the equations we're going to use for chapter 2, 3, 4, and 5. There's a couple little things that we'll add, but if you're looking to try and memorize equations, these are the ones we're basically going to need for the next few chapters. You're always going to have these equations if you have a constant force. So when we do energy, we may need them. So don't ever forget them. If you can, learn them. I've memorized them because I've used them so often. They're not hard to remember, but those are the equations. I always get people that ask me, like, well, what equations do we need to know for exam 1? It's going to be these, a little bit of vector stuff, and a few other little things. But in a sense, these are the equations of motion with constant acceleration, which means that we have constant forces, and that's what we're going to use. So you might want to bookmark this at some point, or put them on a flashcard and keep them with you. Just hang on to them and learn them. And they come from those integrals with constant a. All right, so now let's actually start using this and doing something. And we already kind of did this one, but I want to do it as a sample problem. And we're going to get way more difficult, but for now, as a sample problem to understand how we solve these problems. Okay. So we're told that a vehicle starts from rest, accelerates at 5 meters per second squared for 10 seconds, and we want to know how far does it go. Okay. And there's actually, it doesn't look like there's a lot there. There is a lot there. So basically, and I know some of you had physics before or chemistry, and you're probably going to be like, oh, I don't need to do all this stuff. This stuff is busy work. You need to learn how to do it because this is what I'm testing you on. Your ability to solve an equation or a problem logically. And there are very important steps to take that you need to do to make sure that you understand the problem you're trying to solve. So our algorithm is, number one, draw a picture. I find that I cannot do physics without drawing. I doodle everything. I draw little pictures. It doesn't have to be pretty. It doesn't even have to be the full problem. But what you want is something so that you understand what's going on. So for this problem, I would just draw an arrow, and maybe I'll draw a little car. And I say, yeah, it's going to go that way. Okay, and I know that this is my X direction. And then I start looking, it says it starts from rest. So I'm going to assume that it starts at X is equal to 0, and its velocity initially is 0. That's what this is telling me. If it starts from rest, the velocity initially is 0. In my drawing, I've chosen that it starts at X is equal to 0, and that should be X initial. And I want X final. It's asking me how far did it go? I want to know how far it went. So I want the change in X, or more specifically, I want X final. Okay, this is what I want right here. And I'm also told, and you can draw it as a vector, that A is equal to 5 meters per second squared. Okay, and I might write somewhere like time is 10 seconds, whatever. The point is that, yeah, on simple problems, you probably don't need a drawing. But a lot of times when you're making a mistake and you haven't drawn a picture, if you draw the picture, you'll realize your mistake really fast. You'll realize that you have a sign error, or that you're choosing the wrong angle, or that you've forgotten something, or that you just don't know something. So in general, I'm mostly not going to ask you for your drawing, but it really does help to just make a little small illustration of the problem, no matter what the problem is, okay? So we've drawn this. This step, step 2, writing your variables, is the most important. And the nice thing is they're always the same. I mean, it may be Y instead of X, but they're always the same for these problems for free fall and projectile motion. All you have to write is these 6 variables. There may be one more later, but for now, in one dimension, just write those 6. If you have more than one object that's moving, we're going to be having some like cars driving towards each other. Oh, and I'm sorry. Make sure that you draw or you write a second set for the second. We'll do that in a minute. But for now, step 2 is always list your variables. On a quiz or on homework, on an exam, I will usually ask you, the first part of a problem is give me the concepts and equations that are relevant here, and you usually have to list a couple. We'll talk about that later. But the second thing I always ask is list your variables for me, if it's a free fall problem or a projectile motion, because I want to know that you know what your variables are. So this is our algorithm. Now, what do we know from our picture or our problem? Well, we know that it started from rest. So we can say right away that this is 0. We know that the time is 10 seconds and the acceleration is 5 meters per second squared. we're assuming that we can choose where to start measuring x from. So we can say that x initial is 0. And we don't know this, and we don't know this. But something really important here. We're not asked to find how fast it's going at the end. We're not asked what the final velocity is after 10 seconds. So this right here, we don't need. We need this one, and I'll often box what I need. And sometimes I'll put a line through what I don't. I don't know the final velocity. I don't need the final velocity. That becomes very important in the next step, and you'll see why in a minute. Okay, so the other things to remember is that rest meant that the initial velocity was 0, and that constant velocity means the acceleration is 0. That doesn't apply to this problem that we're doing, but it might apply to your problem later on. Okay, the final step, and I'm going to rewrite these. X initial was 0. X final was what I wanted to solve for. V initial was 0. V final and A. A was, what was it, 5 and 10. And T was 10 seconds. So now we get to the third step. And the third step is choose relevant equations. So we know that we're doing constant acceleration. And the only equations we have are x final minus x initial, v naught t plus a t squared over 2. V final is equal to v initial plus at. V final squared minus v initial squared is equal to 2a x final minus x initial, and x final minus x initial is v final minus v initial, plus times t. Now, here's where this whole thing comes in, this getting rid of v final. In choosing our equation, if we don't have a value for a particular variable, and we don't need to find it, that will tell us right away what equation to choose. Anything with v final in it, we don't want. We don't want to even deal with it because we don't know it, we don't need to know it, we don't want to solve for it. So you can get rid of all 3 of these, and that only leaves us with this equation. Now we know we're going to solve this for x final. So the solution is going to be, we're going to use this equation and these variables and solve for x final. And that's it. That's the whole algorithm. Draw a picture, write your variables, and try to figure out what they are, or note which ones you don't know but need to find, and which ones you don't need to even worry about. Step 3, find the equation that's relevant to your problem. There's a little bit of a trick where sometimes you can solve for something much faster using something you don't know. Like I could actually solve for v final here and then plug it in here to get x final if I wanted to. But what I'm mostly trying to help are those students who have no clue. So if you just write these steps down and follow them, it's kind of the fastest or most logical or most straightforward way of solving any of these constant acceleration equations. And it's what I want you to do, because most of the time you'll know what to do. But every once in a while in physics, you show up and you're having a bad day and you've got an exam and your mind just completely blanks. And if that hasn't happened to you, it may. So when that happens, what I want you to have is a strategy to deal with it. You should all be able to just write down x initial, x final, v initial, v final, a, t, and then try and fill them in. And that's where you start, right? And then, to be honest with you, if you're grasping at straws and you really don't know what to do, start trying to solve for the ones you don't know. Solve for v final, solve for x final. And hopefully you'll get enough progress to figure out, oh, right, that's how I get the final position of this thing. These are really simple problems. Later on, you may need to to use these algorithms when you're kind of lost, and you can use them and you'll get 50% of the problem, right? 50% of the problem is figuring out what to do. The rest of it's actually doing the algebra and solving, okay? So let's actually solve our problem here. We have that these guys are 0. We're going to use this equation. So we're going to use, and I want you, when you do solutions on quizzes or on homework, on exams, I want you to write the equation, first of all, symbolically. Okay, so that means, right, this is the equation I'm using in symbols. Then I know that x initial and b initial are 0, so I can get rid of that term and that term. And you can do that, and that's fine. And that gives me this. You will make less algebra mistakes if you don't plug in numbers until the very end. It'll keep you from making algebra mistakes. It doesn't seem like it, but it's totally true. So solve it symbolically first and then plug your numbers in. So I know that this was 5 and this was 10 squared over 2. 10 squared is 100. So this is 500 divided by 2. This is 250 meters. Please, please, please always put units in your final answer. Units are there to double check that you're getting, that you have your equation right. So if you were unsure if your algebra was correct and you came up with this, you know that acceleration in meters per second squared, this is seconds squared is time. These cancel and I get meters, okay? The reason we use units in physics is we need to make sure that our math is correct, and units are the best way to figure that out. If your math is wrong, your units will be wrong in general. So you'll also find if you're taking chemistry or some of the other mathematically driven sciences, that if you start using units and get used to using units, a lot of times you can figure out the really simple plug and chug equations because you know the units. If I gave you force and I gave you a mass and I asked you for acceleration, force is newtons, which are kilograms meters per second squared. Mass is kilograms, so I know that if I divide A is equal to F divided by M. We'll talk about that more next time when we actually go over Newton's laws, but units are helpful because you don't have to actually necessarily know an equation. You can figure it out by units and what you're given and what you're asked for. Anyway, let's move on to some actual fun problems. Unfortunately, these are all going to be cars. In general form, they're cars, but it could be anything. It could be 2 birds flying in the sky. It could be 2 fish. It could be 2 rockets shot at each other, whatever they are. In these problems, they're all going to be one dimension, and they're all going to have constant acceleration or acceleration of 0. And what we're going to try to do out of these problems, these next couple problems, is figure out how to use the algorithm every time correctly, okay? I didn't put numbers here. I'll make up some numbers, but technically there's only a couple different types of these problems, and we're going to go over the 2 most important ones. Okay, we have one vehicle with constant velocity and one vehicle with constant acceleration from the same starting point. So let's draw a picture of this. Imagine at x is equal to 0, you have, and then it's some x final, you have car 1 or car A. Car A is going that direction with a velocity that is constant, so the velocity of A is 10 meters per second. At time t is equal to 0, it passes this point x naught where x naught is equal to 0. At that same time, at that same position, at x naught is equal to 0, car B begins to accelerate from rest with an acceleration of 3 meters per second squared. I want to know if they, at the same point at time t is equal to 0, the cars are at x naught is equal to 0. I want to know how long it takes. So I want to know t, and I want to know x final. I want to know how long it takes for them to arrive at the same x final point. Now here's something really important. Car B, we're going to assume can accelerate the whole time. We're going to assume that x initial is the same for A and B. A and B, same. And t has to be the same for both of them. The amount of time it takes to get from x naught to x final will be the same for both of them. The distance they travel will be the same. What will be different is their accelerations and their velocities, okay? So our algorithm was draw a picture. We drew our picture, and we kind of thought this through a little bit. That's the hard part of physics, thinking this through, understanding what's being asked of you, okay? The next thing was draw or write our variables. So I want them for A and for B, okay? X naught, X final, V naught, V final, A and T, X naught, X final, V naught, V final, A and T. Now, first things first, start writing things that you know from the question, okay? And further, the first thing we're told is that vehicle A has constant velocity of 10 meters per second. And so its final and initial velocities are the same. They're both 10 meters per second. That means its acceleration is 0. So vehicle A is not accelerating at all. And it starts from 0. We don't know its final position yet, and we don't know how long it takes to get to that final position yet. Now, for car B, it started at rest, has an acceleration of 3 meters per second squared. So we don't know its final velocity. We know it started at 0. We don't know its final position, and we don't know how long it takes to get there. So that's all we have. And notice we're missing a whole bunch of stuff, but that's okay, okay? Because we know what we know, and that will help us start choosing equations and start filling them in. So in a weird way, what you're going to do is you're going to try to fill in this set of variables. That's what you're going to try and do. Now, before I go any further, remember when we said that back here, when we said if A was equal to 0, what happens? Well, we only get these two equations. So let's go back to the problem we're doing, and I'll write those two equations for you right here. We get that for B, x final minus x initial is equal to V of B times T. B final of B times T, I should say. And furthermore, we get that V final of, I'm sorry, I'm doing that wrong. I'm being dumb. Sorry, guys. For V of A final is equal to V of A initial, since our acceleration is 0. So x final minus x initial is equal to, I'm just going to call this V of A. V of A times T, and V of A final is equal to V of A initial. Those were the only two equations we get if the acceleration is 0. Now we know this is 0, so we get that x final is equal to V of A times T. Or we get that T is equal to x final divided by V of A. I'm going to go to the next page and write those. So x final is equal to V of A times T, or T is equal to x final over V of A. Now we need to remember that B only has an acceleration of 3 meters per second and squared, and x naught and v naught of B are both 0. Okay, so we don't have V final. If we go back and look, we don't have V final for B. So we're going to stick to this guy, this top equation for B. And I'll rewrite that. So for B, we have x final minus x initial is equal to b naught of b times t plus a of b, t squared over 2. Now we said this was 0, and we said this was 0. So we get that x final is equal to ab t squared over 2. You could also solve this for t. You would get t is square root of 2 times x final over ab. And I should call this ab. Now, I can do one of two things. I could either set x final is equal to ba times t, and it's also equal to ab times t squared over 2, or t is equal to x final over ba, but it's also equal to square root of 2x final over ab. Okay, and what I wanted to know was x final, and I wanted to know the time. Okay, so I can solve either one of those, whichever one I want. Notice that this one here, I'm going to have to do something weird because I have this under the square root, and I'm going to have to do some extra stuff. If I square both sides, I get x final squared over ba is equal to 2x final over ab, or x final, if I divide through by x final on both sides and multiply by ba, 2ba over ab. T, same thing, if I divide through by t and multiply by 2va over ab. Have I done something weird here? Because I shouldn't be getting the same thing. Something's bugging me. That I've done something weird here. So this is definitely true. 2x final over ab. Oh, 2x final over ab. This doesn't have any x final in it. And this would be 2va over ab. This would be 2va over a. Okay, fine. I also get that t is equal to 2va over ab. And that seems wrong to me. I'm not catching my mistake at the moment. 2x final over ab is square root. Yeah, okay. Maybe I'm just going crazy. So let's double check it and see if I can find my mistake. I said that VA was 3, or was 10. So this would give me 2 times 10 over 3, which is 20 divided by 3, which is 6 point something seconds. I get 6.67 seconds is my time. And my final position, if I use this guy, is 2 times 10 over, which is again 6. Yeah, that seems super wrong to me, but maybe that can't be right. So where have I made my mistake? Let me go back through this really fast because something is wrong and I'm not seeing it. Okay, so for A, I know that A was the car that had constant velocity. X initial, X final, V initial, V final, A, and T. 0, 10, 10 years per second, 0, and unknown, and unknown. And then for B, X initial was 0, X final, V initial was 0, V final was unknown, A was 3 meters per second squared, and T was unknown. So for this guy, I have that X final is equal to A T squared over 2, or T is equal to 2x final over A. And for this guy, I have x final minus x initial is v of a times t, or t is equal to x final over a. That seems right. So how did I get a weird 2 in there? Over VA, sorry. So how did I get a weird 2 in here? Setting those t equations, and I forgot my square root. So I get that x final over VA is equal to square root of 2x final over a. And if I square both sides, I get x final squared over VA squared. Oh, I know what I did. I know exactly what I did wrong. All right, I feel better now. So x final is equal to 2VA squared over a. That's where I dropped the squared. Okay. Sorry, everybody. My brain's not working today. So this equation here should have been x final over VA squared, and that would have given me the squared. So, okay, so this becomes 2 times 10 squared is 200 divided by 3, or 10 times this, and x final, so t is 6.67 seconds, and x final is 66.7 meters. If you divide this, you get that time. If you plug in 10 times 6.67, you get 66.7 meters. If you plug in 3 halves times 6.67 squared, 6.67 times 6.67 times 3 divided by 2, I get 67.7. So, to recap, what we did was we drew a picture, we wrote our variables. Using our variables, we found which equation to use, and we had to find x final and we had to find t. Now, for car A had constant velocity, v, and no accel. Car B had no initial velocity, and a was equal to 3 meters per second squared. And what we ended up doing was using the equations for no acceleration, which are x final minus x initial, is v of car A times t, solving that for either x final or t, and setting it equal to t in car B's equation, since this was 0 and this was 0. So what you ended up doing was using this equation and this equation and using them to solve for either x final or t. And we found that x final was 66.7 meters and this was 6.67 seconds. Okay? Now, why were we able to set these equations equal to each other? Well, again, looking at the picture, they have to travel the same distance when they meet up. So x final will be the same for them if they meet at that point. And they have to do it in the same amount of time. Physically, that has to happen, right? Okay, so if they do that, they're all good and everything works, right? Okay, now, the other side of this equation, how we could make this equation hard is what if they were traveling toward each other? So instead of A and B starting at the same point, they start at opposite points, okay? Now, when we do that, this will be x initial for A, and we'll say that car A is traveling with a velocity of 8 meters per second constant. A is 0. And we'll say that car B is accelerating at 10 meters per second squared. So this is car B. X initial of B, we will say, is unknown. Okay. No, we won't say that. Sorry. We're going to say it's 100 meters, just for the heck of it. So we'll say that this is 100 meters from point. So at some point, this will be x final of A minus x initial of A, and this will be x final of B minus x initial of B. And we need to figure out where this point is. At what point do they meet? If at time t is equal to 0, car B is initially at 100 meters per second. The acceleration is negative because we're choosing x to be positive to the right. And since car B is accelerating to the left, its acceleration will be negative. The hard thing here is that we need to make sure that everything is in the same coordinate system, okay? So we've kind of drawn a picture. Maybe we've confused ourselves a little bit. So what is the next step? Well, the next step is x initial of A, x final of A, v initial of A, v final of A of A, and t. And then x initial of B, x final of B, v initial of B, v final of B, A of B, and t. We're not going to know t yet, so what I want to know is what is x final of B and what is x final of A. I know that this guy is 0 and this one is 100 in this case. I don't know what this is, but I do know that x final of A is x final of B. They will be at the same point when they meet. I don't know what time is. I know that car A is traveling with constant velocity, so this is 0. I know that this was given to me as negative 10 meters per second squared. It's traveling to the left and accelerating to the left. And I know that this is 0. And I hate when my PowerPoint does that. So I don't know this. I don't know the time. I know that these two things are both 8 meters per second positive. Okay. So now what do? What's the next step? Well, I need to find an equation that I can solve for either time or x final of A for A. For car A has A is equal to 0. So we only have V final of A is equal to V initial of A. We're just going to call those VA. We have x final of A minus x initial of A is equal to VA times T. This is 0. So again, we have that x final of A is equal to VA T. Now, this one, we need to find x final of B. And we know that V initial is 0. We don't know V final and we weren't asked. So we're going to use x final of B minus x initial of B is equal to V initial of B times T plus A of B, T squared over 2. Again, V initial of B, since it started at rest, was 0. And what we get is that x final of B minus x initial of B is equal to AB T squared over 2. X final of B is equal to x initial of B plus AB T squared over 2. Something really important here. We knew that x final of A is equal to x final of B, and we're going to solve for time. But we know that x initial of B, it was initially at 100 meters. Okay, so this is 100. A was negative 10 because it was going left. So minus 10 over 2 times T squared is equal to x final B, which is equal to VA times T, and VA was 8. So VA times T is equal to x final of A, which is equal to x final of B. This is 8T. Now, look at this though. We've got a quadratic here. So we've got a quadratic that's 10T squared over 2 plus 8T minus 100 is equal to 0. And you can solve that using the quadratic formula, which is minus B plus or minus, let's call it B squared minus 4AC over 2A, and that'll give you the roots when T is the roots of those. Or we can stop and not solve it that way. and try to solve it for eliminating t, okay? If you want to do it this way, we'll do it this way really fast. So we have that minus b plus or minus b squared minus 4ac over 2a, quadratic equation. This is our a coefficient, is 10 divided by 2. Our b coefficient is 8. So a is 5, b is 8, and c is minus 100. Now, this is minus 8 plus or minus 8 squared is 64 minus 4 times 5 times minus 100 over 2 times 5, which is 10. Whenever you do the quadratics in our class, we will never have a negative number under here. And so luckily, this is actually 2,000. 20 times 100, the negative sign cancel. What we get is we get negative 8 plus or minus 2064 over 10. Now, when I do this, the square root of 2064 is 45.43. So this is minus 8 plus or minus 45.4, let's call it, over 10. And I get two solutions. I either get 53.4 with a negative sign over 10, so 5.34, or I get, what is that, 37.4? 5.4 minus 8 divided by 10, 3.74, or 3.74. Seconds. Which do I choose? Does negative time make sense? Remember, these are giving me my time. They're giving me the solution for t that makes this equation true. Negative time doesn't make sense, okay? And it's a weird problem based on the fact that it's a quadratic, that it has two solutions. So we have to choose the negative time. So we're going to choose that the time is, we have to choose the positive time. That the time is 3.74 seconds, and then we need x final of A and x final of B. And we'll just plug that back in. Now we know they're equal. So x final of A, we said, was VA times T, where VA was 8, and this is 3.74, right? So this is equal to, what is 3.74 times 8? It's about 30. So 30 meters. That means that if we go back to our drawing, this guy will have traveled 30 meters. This guy will have traveled 70 meters at the time where they run into each other, okay? However, note that our position is the same. Our final position is at x is equal to 30. Car B started at x was equal to was equal to 100, okay? 100, x, and why am I writing so badly today? X initial of B, and x initial of A was 0. So let's see if our stuff makes sense. So we get x final minus x initial is equal to AT squared over 2. This would be 30 minus 100 should be equal to A, which was minus 10 divided by 2 times 3.74 squared. This is minus 70. What is this side? It's minus 5 times 3.74 times 3.74. I get minus 70, okay? So it works. We know what x final is. We know what x initial is for A and B. Last thing that we can do is we could ask, what is the final velocity of car B right before it, well, when it gets to this point? And here's a weird thing. So when it gets to that point, we know that x final of B will be 30. X initial of B would have been 100 meters and meters. We know that B initial of B was 0. And so we have this other equation that says B final of B squared minus B initial of B squared is equal to 2a x final minus x initial. These are all b. This is 0, right? So this is VB final is square root of 2a times x final minus x initial. A was minus 10. X final minus x initial is minus 70. So this is 2 times minus 10 is minus 20 times minus 70 is 1400. So 1400 positive. And the square root of 1400 is 37.4. So this is square root of 1400, which is 37.4 plus or minus meters per second. Sorry. So is this going to be plus or minus? So V final of B, when it reaches that, it has to be minus. How do you know? From the picture. We're assuming back in the picture that going to the right, or going to the right with positive, going to the left was negative. We have, if you have the square root of 14, this is equal to plus or minus 37.4, and you have to choose. You guys should know that from math. But the only way to know whether it's positive or negative is if you have the picture in your head, right? So keep that in mind. You can see that these things have already started to get really complicated. And the only way to kind of keep track of them that I can think of is do the algorithm, draw a picture. Well, let's go back back to the algorithm. You can watch this on screen. So draw a picture. For each object, list the 6 variables, and then see if from the question you can fill in those variables. You also may have at a different time later on, the variables change, right? We'll talk about that when we get there. At that point, you need to also remember that constant velocity means that the acceleration is 0, and that rest means that the initial velocity is 0. Then, the next step is, from those, figure out what you're going to solve for, what the question asked you for. In this case, it asked for x final in the problem on the screen right now. So we knew we didn't have b final and we didn't need it, and that kind of tells us which equations to use. And the equations that we have to look at are the constant acceleration equations, assuming it's constant. Since we didn't have b final and we didn't need it, that eliminates the 3 questions or the 3 equations at the bottom here. And we know that we can go straight to here to hopefully get an answer. If you have 2 objects, then you need to do a separate set of variables for each one and realize, is the position the same? The final position the same? Is the initial position the same? Is the time the same? Whatever's the same, you can use that to equate 2 equations together or substitute one equation into another equation if necessary, okay? And that's the name of the game with all of these one-dimensional problems. Now, I believe this is section 5. I told you we were going to talk about free fall. And free fall, all free fall means is take an object and either throw it up into the air or let it drop, okay? It could fall off a cliff. You could drop a pen out of your hand and let it hit the floor. But what is in common with all these things is, sorry, I have a really quick email that I need to answer. What is in common with all of these is that we always choose the center of the earth to be down. So in any problem, if you're dropping a ball out of your hand, right? So you drop a ball and it falls towards the center of the earth. Y has to be positive up, okay? And by positive up, we mean positive away from the center of the earth. G is the acceleration. So the magnitude of the acceleration of gravity, the magnitude is 9.81 meters per second squared. But the actual vector of A points downward, and the actual value of A is negative 9.81 meters per second squared in the negative y hat direction, okay? People always get confused on that. So if I go back to my equations that we just learned, and we're gonna put them in terms of y instead of x, v naught y t plus a t squared over 2. Now, I said that a is negative 9.81 meters per second squared in the y hat direction. This is known as g. Furthermore, it's negative g. G is not negative 9.81. G is 9.81 meters per second squared. You may think I'm being weird about that, but I invariably get people that mess up the signs because they tell me, well, G is negative 9.81, and I'm subtracting it. And I'm like, no, G is 9.81. You're subtracting it because in this problem, we chose y to be positive upward away from the center of the earth. Okay. So when we do that, we get y final minus y initial is v naught of y t, plug in for a minus g. And whenever you see this little g, you assume that's 9.8 or 9.81 meters per second squared. Wiley sometimes uses 9.8. Sometimes they use 9.81. I tend to use 9.81. Later in the semester, we'll talk about gravity. We'll talk about why the acceleration due to gravity, how something's velocity changes if you drop it and it's subjected to the force of gravity. We'll talk about why it's 9.81. But what changes in all of these equations now is we get v final of y squared minus v initial of y is now minus 2g, y final minus y initial. And the last one I'm going to do is v final of y is equal to v initial of y minus gt. If you look on this final slide, for each of these equations, change the x's to y's, change the a's to minus g, and you get these equations here at the bottom, okay? I find this last one is pretty useless, not very important at all, but the rest of these are important. These are the equations of free fall in one dimension with the acceleration due to gravity, okay? So we have 4 different cases that I'm going to talk about. And in the first case, you have an object drop from rest. So you take a ball and it weighs, let's say, 2 kilograms, and you drop it from a height, and the height is y initial, which is equal to, I don't know, 3 meters. So you're dropping it from about 10 feet. And what I want to know is if you drop this ball from 10 feet above the floor, how fast is it going? And what time, or how much time is it in the air? Okay, so draw a picture. This is my y initial, where I drop it from. This is the ground, which is y final. It's going to fall. The acceleration a is minus g, because it's downward. It's in the downward direction. This is my a. And that's all I need. Again, your algorithm is list your variables. The initial of y, the final of y, a is minus g, and t is unknown. So now, my y initial is my height, it's 3 meters. What is my y final? Well, my y final is 0. My v initial, if I'm dropping it from rest, remember that means that v initial is 0. I don't know this, but I want this. This is what I want. So again, same algorithm. You don't have time, and you need it, and you don't have v final and you need it. So if I didn't really care at all about v final, I could ignore it and just solve for time. How I would solve for time is y final minus y initial is v naught y t minus gt squared over 2. This is 0. This is 0. and I get minus y naught is minus gt squared over 2. The minus signs cancel. I get that t is the square root of 2 y naught over g, which is the square root of 2 times 3 over 9.81. That is square root of 6 divided by 9.81 is 0.782 seconds. Now, if you stand on a chair or something to where you're about 10 feet high and drop something, you could start your stopwatch, let's say on your phone, okay? And if you drop it from about 10 feet, it should take 0.782 seconds to hit the floor in your house or outside. So if something falls off the roof of your house is probably about 10 feet. It takes less than a second to hit the ground, and you can test that. Now, how do we find what V final is? Well, V final is V initial minus GT. We now have T, and so we get minus GT is minus 9.81 times our 0.782 seconds times 9.81. I get negative 7.67 meters per second. Why is it negative? Well, it's negative because the acceleration is downward. It's speed, or it's traveling downward with that speed of 7.67 meters per second in the negative direction, okay? And you'll notice that I didn't put the y hat here. I could have if I wanted to, or you could leave it off. I'm assuming you know this is free fall and you know it's in y. Invariably, I'll also get asked, well, wait, couldn't I have solved it this other way? Yeah, you can. You can solve it any way you want. Basically, you can choose whichever equation to start with you want. You can solve for whichever variable you want. You might find it faster to solve for V final before solving for T. Particularly when you end up with a quadratic like in the last problem we did, sometimes it's easier to go and solve it for a different variable and then come back, and then you don't have to do the quadratic. That's totally fine. I'm never going to tell you solve for T first or solve for V final first. It's up to you which way you want to proceed. That also tells you if you're lost, you get your variables down, but you're lost on the equations, start trying to use equations to solve for things. So try to find an equation that you know everything but one variable, solve for it, and then you have that variable. And once you get the one unknown that you don't have, everything else kind of falls into place. It makes these really easy. So we're going to go through the next few. The next one, I'm not going to go through other than to say is, what if I took the ball and this time I threw it down? So instead of dropping it, I threw it with some V initial, right? Let's say V initial was 2 meters per second. Everything else is the same as the last part. So I get Y initial, Y final, V initial, V final, A, and T. I'm going to use that same drawing, so I'm not going to redraw this. This was 3. So 3, I know this is 0. I chose this to be 0 by choosing this to be 3. This was measured, Y initial was measured from the ground up to 3. So that means this has to be 0. And we will always in free fall measure from the ground up, unless you're really good with it. Just assume that the ground, when it hits the ground, it's at Y is equal to 0. So V initial now is negative 2 meters per second, right? I'm throwing it downward in the negative Y direction, okay? That might be important for, do not forget your negative sign. You have to know it's going down. We don't know this. We know this is negative 9.81 meters per second squared. We don't know this. And you know the time is going to be faster or smaller than what we got before because it's already got some initial velocity. Now, when we do this, Y final minus Y initial is equal to V naught of Y T minus GT squared over 2. Now we can't cancel this term, and we would have to solve this as a quadratic by finding minus GT squared over 2 plus V naught Y T minus y final minus y initial is equal to 0. I just moved these two terms over. And then solve it as a quadratic. Well, you probably don't want to do that, right? So what else could you do? Well, you could try to solve for v final first. Now, v final squared minus v initial squared is equal to minus 2g y final minus y initial. Sorry, that's a y. I know that v initial is negative 2 squared. So v final is square root of v initial squared minus 2g y final minus y initial. V initial squared is negative 2 squared, so this is 4 minus 2 times 9.81. Y final is 0, so this is minus 3. This becomes minus 6 times 9.81 times a minus. So 6 times 9.81 is 58.86. So this becomes the square root of 62.86. If I take that square root, I get 8.26 meters per second. And it's negative because it's falling. And so now I have v final. And now that I have this as 8.26 meters per second, I can find the time really easily from v final minus v initial is equal to minus gt. So time is v final minus v initial over minus g. This is minus 8.26 minus 2 over minus 9.81. Time should always be positive. Is it positive? Yeah. It's 10.26 divided by 9.81, both on negative. I get 1.046 seconds, which isn't right. Why is that not faster? Or did I get the time wrong before? Final minus a minus that. Oh, because I'm dumb. This is minus a minus. Sorry guys, I make the same mistakes everyone does. So I get negative 8.26 plus 2 is 6.26 divided by 9.81. I get 0.638 seconds. So my time for it to fall is 0.638 seconds. It's traveling at 8.26 meters per second downward at that time. When I dropped it, it took 0.782 seconds, and it was only doing 7.67 meters per second when it hit the ground. So by throwing it down, it will faster. All right, last two things we need to do on this. We have, what if we threw it up? And imagine that you're able to launch it from ground height with some v initial is 15 meters per second. So you launch it from y initial is 0. It's going to go up and come right back down and hit the ground. Okay, so now things are going to get a little weird. Because say I want to know what its velocity at the top of the motion is and what its max height is. So now I have to change this to two different problems. I have a problem where I launch it and it ends up going to some height. If it starts off at y initial is 0 and y final is some h for max height. And then I have the problem of either when it falls back to the ground and I can find the time up and the time down, or the time to go up and come back down. Remember, this is all in one dimension. So what I want to know is I want to know v at max height, and then I want to know v final and t max, the amount of time it was in the air total, and the time to h. So we're going to do each of these separately. Now, when I launch it, and I said that v initial was 15, remember that y, you just do all these things. We're going to measure this as y final is h and it's positive, and that y initial is 0. Y is positive upward. A is negative g downward. Well, A is g, but it's negative because it's downward. Negative g, which is negative 9.81 meters per second squared. V initial was 15 meters per second positive. Y initial was 0. Time, I don't know, but it's the time to maximum height. Now here's the thing, most important thing about projectile motion. You should already know. Take your pen, if you have a pen in your hand, and toss it up in the air. And what do you notice at the top of its height, at the highest point it reaches? It changes direction and starts falling backward. Instantaneously, at the top of the motion, its velocity is 0. Is it ever really 0? Well, if it is, it's only for the most infinitesimal amount of time. But we say at the top of the motion, when y final is equal to h, v final is 0. Okay, that's really important. That is an important concept to understand. This thing goes up, it loses velocity because the force of gravity is slowing it down. The acceleration due to gravity is decelerating it. It's taking velocity out of it, causing it to slow down as it rises until the velocity changes sign. And then it begins to accelerate it, increasing its velocity downward after that. But for now, we know that v final is 0. At the top of the motion, v final is 0. Out of all this, we can find h. So y final minus y initial is v naught t minus gt squared over 2. That doesn't help us because we have the t's in here and I don't want to deal with those t's. I want to find h. V final squared minus v initial squared is equal to minus 2g y final minus y initial, but y final is h, y initial is 0, v initial is 15, and v final is 0 at max height. So I get negative v naught squared is minus 2g y final minus y initial. Remember, I'm looking for y final, and y initial is 0, so I'm going to get rid of that. And I get that y final is v naught squared over 2g. Okay? This is, if you want a number, 15 squared over 2 times 9.81. And I would get 15 times 15 divided by 2 times 9.81 is 11.47. So I get 11.47 meters. Does that seem good? Yeah, that's about right. If the acceleration is 10, it'll travel a little bit more than 10 before it changes direction because it's starting at 15 meters per second. That's something you'll just learn. Okay, so what I asked a minute ago was I wanted v at max height. That's 0. Max height I just found was 11.47. And then the time, and the time's super easy to find now that we know that v final is 0, because that's just v initial minus gt, but this is 0. So t is v initial divided by g, which is 15 divided by 9.81. Not negative. If you do this algebra, move the gt over, divide through by g. So this is how long? Well, it's like 1.5 seconds, right? 1.53 seconds. So I know that it took 1.53 seconds to go up to its maximum height. Now here's the deal. I'm going to prove it to you, but only if y initial is equal to 0 and y final is equal to 0. The time, if it starts and ends at the same height, the time total is equal to 2 times the time to max height. We can prove that though. So now we have y initial, y final, v initial, v final, a and t. And if these are both 0, and this was 15, and this is minus 9.81 meters per second squared, we don't know what this is and we don't know what this is, but let's look at a few things. We know that y final minus y initial is equal to v final y plus v initial y over 2 times t. These guys are both 0, right? So what we get is that the t to the half cancels away, and we get that 0 is equal to v final y plus v initial y, or v final y is equal to negative v initial y. So since this was positive 15 meters per second, we know this will be negative 15 meters per second. Whatever speed it went up with, it comes down with, right? Secondly, for the time, if y final minus y initial is equal to v initial of y times t minus gt squared over 2, again, these are 0, so I get v naught yt minus gt squared over 2. Then I get v naught yt is equal to gt squared over 2. Divide through by t, multiply through by 2 over g, and you get that t is 2 v naught of y over g. Look at this. What did we find for the time to max height? We found the time to max height was v naught of y over g. So the total time to go up and come back down is double that, okay? Now, without having to deal with max height, you could have solved all this because you know v naught is 15. And that's all it would have taken to find all these things. Pretty easy stuff, right? It's actually kind of fun. There's only a few different types of free fall problems that you can imagine. Is it going up? Is it coming down? Is it starting at rest? Is it going up to max height? Is it not? The hard one is this one. This one's the hard one. If it's got a different max, so let's say you throw it and it goes over a cliff, and you're close enough to the cliff that you can treat them as one-dimensional. So you don't care about the x. So if y initial was, say, 5 meters and y final is 0 meters, so you're throwing something off a roof, but you're throwing it up and then it's landing on the ground, you can do one of two things. You can treat this as a problem where it goes up to max height and y initial is 5. If you do this, though, note something happens. Y final minus y initial, v naught t minus gt squared over 2, and v final squared minus v initial squared is equal to minus 2g y final minus y initial. Now the y initial doesn't cancel. The v final at max height is still 0, and you get v initial squared is equal to 2g y final minus y initial. But when you divide through by 2g, you get that y final is equal to y initial plus v naught squared over 2g. So divide through by 2g and then add y initial to both sides. So you get the max height plus whatever in, let's say, this thing long with some v initial, I don't know, 4 meters per second or something positive. You have to add the initial height in. Now, if you claim that this was 0, right, you could say that this was 0 meters and that this was negative 5 meters, and then you could just find this and you wouldn't have this term. But if you have that term, it's there, no big deal, right? What then you have to do, though, is if you found the time that it took to go up here, because now you've got the height, and you could find the time from here, let's say, or whatever way you find the time up. The time down, you're going to have to find as if it starts and free falls, and v initial is 0, and y final is whatever it is in here. Y initial is max height, okay? So you could treat, to find the total time, you could treat the time up plus the time down, or you could do it with y final minus y initial is v naught yt minus gt squared over 2, where now these are actually the full total trajectory that it took. That's a little bit more complicated, only because you're going to have to do a quadratic here. I like to avoid quadratics because I mess them up or I forget like where the sign goes. But you can do them as a 2-part problem and find the time up and the time down, or you can do them as a quadratic and find the total time. The difference is that when you do the 2 different times, you're going to have a different y initial and y final when it goes up and a different y initial and y final when it drops. So other than that, this stuff is actually kind of fun because you can actually try this stuff. You can figure out how fast something would fall going off over Niagara Falls. You could find out how fast a boat falling over Niagara Falls would hit the water at the bottom if you knew how high they were. We're neglecting air resistance. We're neglecting some other things that would normally be going on that we'll talk about way later. But essentially, these equations will tell you how fast something will hit the ground if you drop it. And they'll tell you how high up something will go if you launch it with a certain initial velocity. 4th of July isn't for a few, well, like 6 months now or whatever. But rockets from 4th of July, fireworks flying into the air are always kind of cool to see because they launch with an initial velocity. And they generally don't have too much thrust. They get launched into the air, and then you can tell how fast they left the ground by how high they go. And then you can tell how fast they're going to hit the ground because you know at the top of their motion, their velocity is 0. So we could have a vehicle or an object moving with constant acceleration and these equations. We could have it moving with constant velocity, no acceleration. We get these equations. We could compare two objects, one that's got acceleration and one that's got velocity, constant acceleration and constant velocity, and figure out where they meet or how far apart they end up or blah, blah, blah. And then free fall is using constant acceleration, but we're in the y direction. Y is up, positive, away from the Earth. The acceleration is negative, down toward the center of the Earth. It has a magnitude of 9.81. And you just substitute for A, negative 9.1, 9.81, or negative G in everywhere you see A in these equations. And you get these equations. So change X to Y, change A to negative G, and that's it. These are the equations for this chapter. They're pretty simple. Go through and do some of the sample stuff. And you don't need to memorize these equations, Gabrielle. I will give you an equation sheet, plus you'll have your notes. You're gonna have your notes for your exams if you want them. I'm cool, you guys are at home. I can either try to stop you or I could just say, hey, yeah, use your notes. That doesn't mean the exam's gonna be any harder than it would be if you were in class. I just want you to, I want you to demonstrate for me on exams that you know a problem-solving strategy for when you get in trouble. And so I'm going to have you on an exam. I'm going to give you a question and break it up into parts like, hey, give me the variables, list the variables, and list the ones that you don't know. And then the next part will be, give me the equations that you need, you know, symbolically, find the time it takes to reach max height, let's say. And then the final question will be, well, okay, how long does it take? Like, give me an actual numeric answer at the end. And the numeric answer part's maybe, you know, 5% of the total question. The important part is that you have a strategy and a logical algorithm or recipe or set of steps that you follow, and I'm going to lead you through those by hand. Basically, instead of just giving you an answer and having a rubric that you never see, I'm going to take you through what the rubric's saying. Did you give the correct equations? Did you list the variables? Did you draw a picture? Did you do the algebra correctly? Did you get the right answer? And on my exams, there's usually 5, pretty much 1 per chapter. So exam 1's usually 5, exam 2's usually 5, and exam 3, the final exam, is usually 6. We'll talk about that though. I don't want you guys too nervous about it. You'll get practice exams and we can talk about that there. But you're gonna get homework tonight on free fall and one-dimensional constant acceleration. I probably won't give you some homework problem that has some weird position function that you need to take the derivative of, because honestly, doing all those crazy derivatives is why you're taking calculus. In the real world, in real life, these equations govern the motion of something falling. And you can see that that position function is really simple. This is the position function in terms of t. X is equal to v times t plus a over 2 times t squared. That's as hard as it generally gets. So you'll get a homework. It'll have a few different questions. Make sure you try a few of the sample problems, go through a few of the examples in the text, and try and do it yourself and see how it is, how it goes. Hopefully it'll work out for you. And then on Thursday, we're going to have a vector lab. It sucks. It's an awful lab, but you're just going to have to draw some vectors and measure them with a ruler and add them and subtract them and stuff. I hate that lab, but we've got to do it. It's important for some of you. Some of you don't know your vectors. So on Thursday, you'll have a vector lab. No quiz on Thursday. If you didn't take the quiz yet, take that quiz, please. It's adding vectors. It's available now. And then I'll have your grade up. I'll give you your 50 points if you sent me the IOLab picture by email or submitted it. And I'll grade the graphing labs by Thursday before class. So everything you've turned in and your syllabus and any quizzes, everything you've turned in should have a grade on it in Canvas by Thursday. Okay, I'm going to end the recording, but I'm still here, so hold on one sec.